Greetings, fellow students. It's Doug Summers talking to you from Ottawa, Canada. I'm a music composer and I'm taking this course to help with the production of the music which I make. I was going to start today by talking about frequency, amplitude, and timbre, and to use an example of a piece I'm actually working on today as a way of talking about those three aspects. First, let's just give a couple of seconds a quick listen here. So you hear that at the start, of course, it was very quiet. We heard then a bit of a drone and some wind sound, and then a plinking kind of synth type sound, which came in 4 times. So let's start by looking at the graph here. This is representing 2 things. The first thing is time, going left to right, and the second thing is the height of the waveform here. Now the wave is a reflection of what was recorded by the microphone. So I could take any part of this and I could expand it, and you'll see the squiggles as the sound waves hit the microphone and cause the microphone to vibrate back and forth in sympathy with the sound. That gets captured, turned into voltage, and here it's represented on the computer. The further that the sound deviates from its rest state, with i.e. being silence, the louder the sound, the greater its amplitude. So the amplitude is a measure of how far from rest state it is. If you take the rest state to be this 0 line, then these signals representing the sounds going farther from that 0 state represent the amplitude. You can see here the amplitude of this part of the signal is higher than over here. The second thing that this shows is it shows actually what's happening with respect to the frequency. So you can see here, you can actually see the little squiggles here which represent the sound of that wind and the drone. But when the synth comes in with that kind of plinking high sound, if I expand that, you'll see that there's actually a lot of information within it. Here's the wind, again expanded, and here is that plinking synth. In each one of these units of time, you can see that actually the number of variations in the sound wave in terms of compression and rarefaction is actually not that much compared to in the same period of time over here what's happening during that synth sound. So the number of these variations per unit time is the frequency, and the more, the higher the frequency. So there's a higher frequency component in here than there is over here. Frequency is measured in hertz, which is the number of times that the sound will go from compression to rarefaction, or the voltage will go from positive to negative in a unit of time, being a second. So 1 hertz would be 1 time a second. 500 hertz would be 500 times a second. So you'll see that here the frequencies here are lower than over here. The last thing which I want to talk about is timbre. And to do that, I'm going to bring up a new graph. Okay, I've now opened a new window on the top here, which is a sonogram, and it measures things a little bit differently than what we've been looking at, which is in the bottom pane. The sonogram shows time, just like the bottom, going from left to right, but it actually shows now frequency, the various frequencies that are present in the sound, going from the bottom of this window up to the top. The top is higher frequencies, the bottom is lower frequencies. And what you notice is that we have all of these marks which are in yellow and green. The closer the mark is to a bright yellow or orange, the louder the sound is, i.e. the higher the amplitude, because higher amplitudes to our ears in terms of sound relate to something which is louder than something which is a lower amplitude. So things here which are yellow or greenish or yellow-green are going to be higher amplitude. In fact, we've got a little bit of orange in there, which is even higher still. But the other thing is it shows the amplitude of the various frequencies that are present in the sound. So you'll notice, again, we're going to play this, that as the synth comes in with that plink kind of sound, there are all kinds of high frequencies which are present and are also with a reasonably loud amplitude, or relatively high amplitude, and therefore a loud sensation to our ears. Let's just have a listen to this again. So you'll see that as the plink sounds happen, the computer has detected that there are a lot of higher frequencies as components within that. And these components are often called either overtones or partials. So really the sound here, it doesn't represent just one frequency, but actually represents many frequencies that we hear all together. And that combination of all of those frequencies with the various amplitudes that each one of those frequencies has, and how that amplitude and frequency pattern changes over time, is called timbre. And so things like this plink sound from the synth can be differentiated from the wind sound in the drone before it, not just by our ears hearing it as a different sound, but you can also actually see it here as a different sound because of the different kinds of overtones or partials that it contains. And that, because of the way our brain has been trained, allows us to recognize certain sounds, because we can detect by virtue of what partials exist, probably what kind of instrument made the sound. To finish this up, I'm adding one more chart now. This one will show you the frequency against amplitude. So what we're looking at is, you can see a little bit of a representation of a piano keyboard down here, middle C right here. So all of these would be frequencies which are higher than middle C in terms of pitch, and these are frequencies which are lower, down to the lowest note on the keyboard. And the height here of this line represents the amplitude that's found of those various frequencies. So it's yet another way of looking at things, which is a little bit like the sonogram, but different. So let's just again play this very quickly and have a listen to what happens to the graph. See, as the sound comes up, the amplitude goes up overall. And as those synths plink, you'll notice that in here, the higher frequency components are moving up in terms of amplitude as each one is played, just in the same way as we saw in the sonogram. We have higher amplitude, and over here we have higher amplitude. You can see higher amplitude in the higher frequencies. Let's listen to that one more time. So this is a what's called a spectrogram, which shows you the spectrum of sound from the lowest frequencies over here to the highest frequencies over here, and the amplitude and how that varies. So we've really covered three things then. We've covered both amplitude, we've covered frequency, and we've covered timbre. Frequency is the number of times per second that a sound changes. Amplitude is the deviation of that waveform from its rest state or zero state. Higher amplitudes to our ears sound like things which are louder than lower amplitudes. Higher frequencies sound like higher pitches to our ears than lower frequencies. And finally, timbre is the combination of many frequencies that we hear at the same time, each of which has its own amplitude, and that amplitude and the frequency component may change over time as well, just as we see in this sonogram. But it's actually these kinds of complex combinations of frequencies that our brain has become very adept at hearing, and being able in turn to recognize what the probable source of that sound is, whether it's a voice, a trumpet, a string, or even the wind. So thanks very much for listening. I hope you got something out of this, and we'll see you on the next one.